We said before that a binomial random variable was a special type of discrete random variable. And what we want to say now is that this Bernoulli random variable is a special kind of binomial random variable. And the difference is just that with the Bernoulli random variable, we're modeling exactly one trial, whereas with the binomial random variable, we were modeling many trials. So before, if we used a binomial random variable to model the probability of flipping a certain number of heads on a larger number of coin flips, we might have been flipping the coin 5 times or 10 times or 1,000 times. We had many trials. When we use a Bernoulli random variable, we drill that down to just one trial. So all we're doing here is flipping a coin one time. And in that scenario, we can use a Bernoulli random variable to model probability. We can also, of course, build our Bernoulli distribution, which will be a visual representation of the probability associated with that Bernoulli random variable. The way that we accomplish using this Bernoulli random variable is by defining success as a 1 and failure as a 0. In other words, we assign numeric mathematical values to these concepts of success and failure. So if we're flipping a coin one time and we're looking at the probability that we flip heads, we would define flipping heads as a success and therefore as a 1, and everything else, in this case flipping tails, as a failure or 0. If we're rolling a 6-sided die one time, we have one trial, we could define success as rolling a 2. So rolling a 2, we would sort of assign this value of 1, rolling anything else. So a 1, 3, 4, 5, or 6 would be assigned a failure or a 0 value. It's really this idea of distilling down success and failure to these values 1 and 0 that makes this Bernoulli random variable unique and useful. So if we stick with our example from earlier about the rideshare company, where we defined success as a driver arriving within 10 minutes of the moment when the passenger requests the ride, and failure as a driver taking longer than 10 minutes to arrive after the ride request, we said that the probability of success was 75%, which means then we know that the Bernoulli distribution looks like this. We know this right away. This is just like the binomial distribution in the sense that we have the set of discrete countable outcomes along the horizontal axis. In this case, we're using this Bernoulli random variable, so we assign those values 0 and 1. So with the Bernoulli distribution, we will only ever see 0 and 1 along the horizontal axis. We will always see both 0 and 1 and never any other values. And then along the vertical axis, we model probability. So using that rideshare example where we said that the probability of success was 75%, then here at 1, we have a 75% probability. And since 0 is the probability of failure, just like with the binomial random variable, if we define the probability of success as p, then the probability of failure has to be 1 minus p. Sometimes we write that as q. But in this case, success is 75%. So 1 minus 75% is 25% or 0.25. And so we can go ahead and graph in here 0.25 for this probability of failure or the probability of this idea of 0. So in this Bernoulli distribution, of course, just like other distributions, these two values here, the 0.25 value that we see here and the 0.75 value that we see here, these values are always going to sum to 1, just like our other distribution. We're just always going to have only these two values represented, 0 and 1, as failure and success, respectively. Now, once we know that we're dealing with a Bernoulli distribution for a Bernoulli random variable, just like all of our other distributions, that unlocks for us formulas that we already have for mean, variance, and standard deviation. For a Bernoulli distribution, here's what those look like. These are actually adapted directly from the corresponding formulas for a binomial random variable. The only difference is that they're incorporating these values of 1 and 0 for success and failure. You can imagine here, with this rideshare example, if we wanted to find the mean for just this one particular trial where our chance of success is 75% and we have these values 0 and 1, we would find the mean or the expected value by taking 0, multiplying it by the 25% chance of getting 0, and then we would add to that the product of 1 and 0.75. So our mean would actually look like 0.25, so 0.25 times 0 plus 0.75 times 1. This would be our expected value. If we have these discrete values 0 and 1, we have a 25% chance of getting quote-unquote 0 and a 75% chance of getting quote-unquote 1. And so this is our weighted mean, our expected value. Of course, we get 0 from this first term, and we get 0.75 from the second term, so we get 0.75. And what we see is that this value here is equivalent to the chance of success we defined earlier, 0.75, or the chance of getting a 1 here, 0.75. And that's always going to be the case because this 0 value here is going to zero out this failure term, which is why we're always going to be left with a mean equal to p, the probability of success. So for a Bernoulli random variable, the mean will always be equal to the chance of success, p. Compare that to the binomial random variable, where the mean was equal to n times p, where n was the number of trials and p was the chance of success. This makes sense also when we think about adapting it this way, because now with the Bernoulli random variable, which we're saying is a specific kind of binomial random variable, we only have one trial, and so n is equal to 1, which means we end up with a mean of 1 times p, which of course is just p, and so of course the mean for the Bernoulli random variable is going to be equal to just p. And we can use similar logic to get the formulas for variance and standard deviation for the Bernoulli random variable as adaptations of the formulas for variance and standard deviation of the binomial random variable. So, for example, remember to find variance, when we have a discrete random variable, we take all of the values that our variable can take on, so in this case 0 and 1, and for each one we subtract the mean. Well, our mean is p, so we would take here our first value of 0, so we would say 0, we would subtract the mean, which is p, and then we would square that value. So this is the square difference between this particular x sub I and the mean, and then we multiply this by the probability of getting a 0. Well, in this case, that's the probability of failure, 1 minus p. So we multiply that by 1 minus p. And we do this for every value that x can possibly take on. So the only other value here is 1. So we add to this. Here we have 1 minus the mean. We square that difference, and then we multiply this by the probability that this value occurs, which in this case is 0.75. It's the probability of success. It's p. So we multiply by p. So this is the sum that we find for the variance. And when we simplify this equation, here we get 0 minus p is a negative p. Negative p quantity squared is positive p squared. So we could say p squared times 1 minus p, and then here we have p times 1 minus p quantity squared. Well, when we expand 1 minus p quantity squared, that's like saying 1 minus p times 1 minus p. This goes back to algebra. We have to multiply our first terms, 1 and 1. So 1 times 1 is 1. Then we multiply our outer terms, 1 and negative p. 1 times negative p is negative p. Then we multiply our inner terms, negative p times 1 is a negative p, and then our last terms, negative p times negative p is a positive p squared. And when we simplify, again, this is all just algebra, we get p squared times 1 is p squared. P squared times a negative p is minus p cubed. We'll say plus p times 1 is p. Here, we have minus p and minus p, that's a minus 2p. So when we multiply p by minus 2p, we get minus 2p squared, and then p times p squared is p cubed. We get our negative p cubed and our positive p cubed to cancel with each other, and then we're just left with, we'll start with this p here, so p, and then we have p squared minus 2p squared is a minus p squared. Or we can write that as the variance is equal to, when we factor out a p here, we get p times 1 minus p. In other words, we rewrote p minus p squared as p times 1 minus p. And you see here how we build this formula for variance that we already established over here as the variance of a Bernoulli random variable. Now, if you're not super comfortable with algebra, that's okay. All of these steps in the middle here is just a bunch of algebra to prove to you that we can get from this first equation here that we built from what we already know about variance down to this equation here to prove to you that this variance formula works, that it's true, that it makes sense for a Bernoulli random variable. But if all we do is walk away from this lesson understanding that the variance of a Bernoulli random variable is given by this formula here, then that's totally fine. This is really the main takeaway. We want to understand that in order to find variance for a Bernoulli random variable, we use this formula here. In our case, that means that variance is equal to P, which is 0.75 times 1 minus P, or Q, the probability of failure, which is 0.25. That gives us a value for variance of 0.1875, and then standard deviation is always just the square root of variance, so the square root of 0.1875, which is approximately equal to 0.4330. And so we're able to calculate the mean, variance, and standard deviation of a Bernoulli random variable. So the takeaway here is that we're interested in drilling down on this idea of a Bernoulli random variable because the thinking behind it is interesting. What we're really saying here, let's take our rideshare example, where we're saying that there's always a 75% chance that a driver arrives within 10 minutes of the ride being requested. We're saying that if we distill that down to just one trial, that if somebody requests a ride within our ride-sharing app, that there's a 75% chance that a driver will arrive within 10 minutes for that particular ride. But of course, similar to some of the other distributions we've looked at, it's really nonsensical to think about one particular driver arriving 75% of the time. One particular driver is either going to arrive within 10 minutes, success, or not, failure. One particular driver will always take on one of those two values only and nothing in between. They will either succeed or fail. We can always code them as specifically a 1 or a 0, and every single individual driver we pick will always be a 1 or a 0. No one driver will ever fall in between 0 or 1 as a 0.4 or a 0.637 or a 0.75. They will always be a 0 or a 1 individually. And yet we're saying that the probability of success for every single driver is some value between 0 and 1. It is 0.75. So the whole goal here is just to understand that while every driver is only going to be success or failure, they're only going to be 1 or 0, they're only going to be on or off, they will only ever take on one of two values. At the same time, we associate with them this probability of success that is some value in between those two exclusive discrete values. And every single ride has that same probability of success P of 0.75, even though each individual ride always gets coded as a failure of 0, the driver doesn't arrive within 10 minutes, or a success of 1, the driver does arrive within 10 minutes.